to speak is Ian MacDonald, who is a professor of oceanography at Florida State University with over 30 years of experience with natural oil seeps and oil slicks in the Gulf of Mexico. He was part of the foundational work on natural seeps in the Gulf as the discoverer of the Bush Hill natural seeps, the Brine Pool NR-1, and the asphalt volcanoes of the southern Gulf of Mexico. He will be describing how surface oil is tracked, specifically what technology and techniques can be used to quantify oil spill and assess their impacts. And this will include a discussion of satellite remote sensing, drones, and data integration. Ian's fun fact is he's an avid woodworker and is writing a science fiction novel about the Earth 6 million years into the future. So, with that, Ian?
Thanks, and thanks to Sea Grant for inviting me and all the participants here. It's so great to see such a full room and so many people participating online. So I'm going to be talking about surface oil in the Gulf, and I'll come back to this photograph at the very end because this is from an oil spill that happened well after the Deepwater Horizon, in fact, back earlier this year. And this is a picture from a paper just published by Helen White and others in the Oceanography magazine, and it describes a variety of different techniques, and I recommend that, and I'll be putting a copy of this publication online to make it available for you. But most of the gadgets that we've seen and most of the concern so far has been in this deep water region of the oil spill. But what I'm going to be talking about specifically is the oil on the surface and the ways that we use remote sensing from aircraft and satellites to detect this oil. Deepwater Horizon released a tremendous amount of oil, and as a rule of thumb, about a third of that oil was distributed in this deepwater plume that we've heard about. Two-thirds of the oil rose to the surface, and about a third of it evaporated within 24 hours or so, and that left a remnant, approximately 33% of the oil, which drifted on the surface. But it was that oil which created a lot of this marine snow that we've been hearing about, which damaged fisheries, and which went ashore across about 2,500 kilometers of the Gulf Coast. So this is an important component of a spill to track, and using remote sensing and other techniques can hopefully give us a better method for doing this. So I'm going to talk about oil spill methods. I'm going to discuss where remote sensing fits in because it has a specific sort of niche to fill across the broad spectrum of oil spill response. I'll give you a little flow chart, which is my idea of how this works, and then I'll talk about lessons from the Deepwater Horizon. The problem of thickness, how do we estimate oil thickness using remote sensing techniques, and then I'll conclude with some cutting-edge stuff to do with drones and technology. And I should say right here that like Vernon, I'm a member of the Ecosystem Impact of Oil and Gas in the Gulf ECOGIG consortium, and a lot of the work that I'll show you was also funded and sponsored by the National Resource Damage Assessment process, and those results are now available. So this is my idea of the cycle of remote sensing applications as applied to a unique oil spill. So the first thing that remote sensing can do is in the open ocean, it can detect that there is oil or some anomalous target present in the surface ocean. And questions can be asked and to some extent answered. Is this a genuine spill? Is this sargassum? Is this a natural seep? Where is it happening? Is it ongoing? Is it something that needs to be concerned with? And that leads to, there we go, evaluation. If we decide that it is a spill, what's the quantity? What's the rate? Is it flowing rapidly? Has it stopped? Are we tracking a finite event? And can anything be done? Is it actionable? This question of actionable oil comes back again and again. Okay, so let's assume that we've detected it, we've evaluated it, it is an actual spill, there's a certain known amount, then there's a tactical response, and this is where our many friends in the Coast Guard are going to play a role in actually deploying assets, tracking the oil, trying to contain or otherwise mitigate this spill. So this is all sort of while the oil is out there and while it's floating. But after that sequence is completed, remote sensing plays an important role in assessing the amount of injury and the damages which were generated by this oil. And so what typically happens with remote sensing, and what I'm going to talk about in the remainder of my remarks, is the way in which that remote sensors and analysts have to go back and look at the data that were collected and reevaluate it. So we're not trying to determine if it was a spill, we're trying to determine the time series and where it went and where it was at different times to try to say, you know, where did the oil intersect different resources? And what kind of impact and then finally, what can we learn that will help us better respond to future spills? So this is my idea of a little cycle here. Okay, so now we shift to the Deepwater Horizon. This is an image taken in early June. This is well after the spill had started. The first spill was in about the 20th of April, I believe, when the vessel sank. But now the responders have gained the confidence to do this bold thing, and they've cut off the risers, and they've allowed all the oil to come out of a single point on the bottom. And this event that you're looking at here, I argue, geologically is unique in perhaps Earth history. There have been natural blowouts in deep water before, but typically they tend to be self-limiting. So here you have a pipe going down another 4,000 meters into below the surface of the bottom of the ocean and tapping into a reservoir and allowing that oil to escape from that highly pressurized, high-temperature reservoir and hit the water. You know, with an instantaneous change going from, you know, very high temperature, high pressure into the open ocean. And this event is not natural in any way. And so understanding how this oil behaved, you know, is a non-trivial question, and a lot of research and attention has been properly focused on trying to anticipate what happens. But the oil, when it was in this position, when the responders had cut this off, this gave them access to all of the oil that was coming out, and this was the time that they were able to actually inject dispersants into the subsea plume. And as I'll show you, this had consequences for the dispersion of the oil and its fate in the surface ocean. Okay. The first question is how much oil was coming out, and it's kind of an unpleasant but a true fact so what you have here in the blue line is the unified command estimate of the rate of the spill. And then these are estimates by various researchers, including somebody named MacDonald, who predicted, looking at remote sensing data and other data, that the rate at which the oil was coming out was actually very different from what was being told to the public, and perhaps what was informing the overall response efforts. So one would hope, you know, looking at this, that a lesson learned would be that we could use remote sensing, we could use underwater techniques such as Vernon has described to come up with a better idea of how rapidly that oil was coming out of the bottom. Because I think one of the things that we did learn from this is that is a crucial piece of information to inform and empower the overall response effort. What are different kinds of remote sensing techniques? I'm not going to spend a lot of time talking about the different satellites, but I want to give you a basic division into passive and active remote sensing. So passive remote sensing, in my definition, is taking a picture, looking at the wavelength of material that is floating on the surface, looking at the response of the ocean surface itself. And so what you're looking at are a variety of different responses, but there is no sort of active insonification or active interrogation of the ocean surface. But these data, and this is something called Aperture, which is a multispectral scanner that was flown on a NASA aircraft, and it was able to pick out, this is a Deepwater Horizon, and they were able to pick out areas of thick oil and thin oil, and then this could then be compared to other types of remote sensing, so other types of data. So optical remote sensing gives you a picture, much like we see, enhanced by a variety of techniques that shows what's on the surface of the ocean. The other type and what you get from this, so this is a picture generated from an ensemble of different optical remote sensing devices that shows the distribution of oil on a specific day, May 17th, 2010, where many different sensors were able to collect synoptic data over the spill. And what it shows are the areas of thick oil. And so in a perfect world, we would have this every day, every hour during a spill so that resources could be targeted, actions could be taken. Unfortunately, this sort of picture was not actually generated until years after the oil had stopped flowing. Optical remote sensing also has a limitation of clouds. But there's another technique, which is synthetic aperture radar, which allows you to see through clouds. So this is the same image taken from the MODIS visible light satellite, and then here we're seeing a synthetic aperture radar image of this same area. And you can see that the radar is able to see right through the clouds, and we can see this very large area of oil generated from the Deepwater Horizon release point, which is somewhere right around in here. So this use of synthetic aperture radar is very effective for looking through clouds, and it gives you a good idea where the oil is. And so this is something that we've worked on in my laboratory for some years. And what you're seeing when you use radar to detect floating oil is not the color of the oil, but the effect that the oil has on the sea surface. And this is something that Brian alluded to earlier in his talk. The ocean, under the effect of wind, is going to have ripples and roughness to it. And that roughness causes the incoming radar to scatter and look relatively bright. But where the oil is floating, that surface roughness tends to be dampened out, and you get a slick. That's why they call it a slick, because it's smooth and shiny, and it actually reflects visible light and radar energy away from the sensor, and so that in a remote sensing SAR image, the dark places here are where there are surface slicks. Now these slicks, as it happens, are not oil spills. These are natural slicks generated by normal natural seeps in the Gulf of Mexico. But you can see that the slicks they generate are quite long and quite distinct. The problem that we have as remote sensors is to take a picture like this. This is about 100 by 100 kilometers. It's about a 100 megabyte file, and somehow translate all of these images, all these slicks, into something that we can use in an objective way. And not to go into too much detail, but what we basically do is make a training set where we evaluate each pixel in one of these images, and we say that it's clean sea or floating oil. And experts go through and they train the algorithm with thousands of examples. And so when you're done and you have an effective algorithm, it automatically, in a matter of minutes or so, takes an image like this and cranks out a binary image of where the oil was. So this technique, texture classifying neural network algorithm, was developed in our lab to look at natural slicks, but it then became available and became a tool that we used to look at the Deepwater Horizon spill. Another technique that we used was the oil emulsion detection algorithm, and what this does is it compares the return from these layers of floating oil and looks for intermediate values. And when we have an intermediate value, that some of the radar energy is actually being absorbed by the floating oil, and so that thicker portions of oil will have a slightly lighter return or less intense return than the normal. So in this region here, you see oil, there's oil everywhere, and where these red dots are, our algorithm indicates that we had thick oil. So during the Deepwater Horizon, and we used a variety of techniques, including the avarice that I referred to before, and also data from the burning operations, which provided a lot of real-time surface data, to predict that thick oil was 70 microns. We call anything that's 70 microns or more thick oil. Well, 70 is not very much. A human hair is about 100 microns. But if you have many, many kilometers of that, it adds up to quite a lot of oil. So this is what I'm going to show you next is a distribution of where the oil. So this is during the Deepwater Horizon, the international treaties were invoked, which allowed all of the available satellites up in space to be pointed at the Gulf of Mexico during the spill. And I think that there has never been a time in the past, and we hope that there will never be a time in the future, when such a relatively small area of the ocean had so many assets looking at it. There were about 170 or 180 SAR images, synthetic aperture radar images, collected over the 100 days or so of the spill. And our group was charged by the National Resource Damage Assessment to go back and look at these data and try to figure out what they told us about the oil. So the problem is that we don't see all of the spill in every image all the time. And our insight was to take each image and treat it as a statistical sample of the larger spill, much the way you would go out and query 1,500 randomly chosen individuals about who they're going to vote for in the next election and form from that sample a picture of what the electorate wants to do. We did that same thing with satellite images over this spill. And so what I'm going to show you now is a movie. It's the oil spill in a minute, and it goes through and shows you not a model, but what our SAR prediction, interpolated prediction every 12 hours of where the oil was. And the units are in cubic meters per square kilometer. So the other thing you'll see the oil coming up and then moving around under the influence of changing wind and current. You're also going to see little dots that appear, and those are where oil was burned, and you're going to see little green lines that show up. That's where dispersant flights were applied on the surface. Oops. Okay, here we go. So we're moving, and you can see the little lines showing up there, little dots where the burning operations are taking place, and you see how the oil is continuing to arise. But there are times when the oil drifts up, according to our model, according to our data, onto the coast, and then finally the Hurricane Bonnie comes through, Tropical Storm Bonnie comes through and disperses it all. So that was very quick. Would have been nice if the actual oil spill had gone by so fast. But then look at this impact area where all of the dispersant flights landed. So this is where we might expect marine snow and other things to have formed. And then this was the average volume over space from Deepwater Horizon. And so, the actual amount of oil in terms of cubic meters, the most we saw as an average was somewhere between 2 and 4 cubic meters per square kilometer, but that's quite a lot of oil over a 100-day period. All right, so what happened to this? The impact of subsea dispersant, came in starting about 1 June when they were able to cut off that riser. And then this is our picture, our time series, adding all those gridded data sets together. And this is our picture of the area of oil-covered water over the whole period. And you can see that it rises to a peak, decreases, and then goes up again. All right? And the peak periods were the 23rd of May and the 18th of June, and you can see that there's a lot of variation in here, secular variation, which doesn't seem to be tidal or otherwise. So this is the area of oil-covered water. The maximum was about 30,000 square kilometers. Then this is the area of oil-covered thick waters, so this is our thick oil, and you can see that there's an increase on the 23rd of May, and then it falls off and then steadily decreases. Okay, if we integrate the volume of oil and oil emulsion over time, we see that it rises to a peak and then decreases and then goes up like that. And the interesting thing is, if we compare the volume on the surface to the area it covered, there's a real difference. And our take-home message is that between this period and this period, the volume of oil on the surface decreased by about 20%, but the area over which this oil was distributed increased by about 50%. So the remaining oil was distributed over a much larger area. Why did that happen? Well, the answer is probably dispersant application. Let me skip that slide. All right, I got just a minute or so left.
No, you're okay.
I'm okay. All right. And I wanted to talk about some of the other tips. So that, that's an important fact, this idea that we spread the oil out, and that's a trade-off. And one of the things that we've discovered as part of the National Resource Damage Assessment process is that very small amounts of oil in the parts per million range can have very deleterious effects on planktonic organisms. They affect the hearts of developing fish. They impact a variety of different planktonic organisms. And so spreading it out over a wide area might be aesthetically pleasing, but the trade-off may not necessarily be good, at least for the planktonic ecosystem. Essentially what happens is that you shift the impact of the oil into the lower trophic levels. So just a little bit more on techniques. This is a picture of where we find natural seeps in the Gulf of Mexico. There are about 1,000 natural seeps distributed everywhere. These are healthy ecosystems, lush, diverse organisms exist where the oil is coming out. If there's sufficient time, nature and evolution can respond to the provision of oil and make use of it. But it also gives those of us who are interested in oil floating on the water a continuous source of experimental data, because we can look at these natural slicks and use our techniques to try to determine where we're seeing oil. And I've got students that are working on this. And one of the things that we've been using to try to improve our understanding of where the oil is an autonomous surface sailor. This is called Sail Drone. This guy goes out, it's released, so they let it go in Gulfport, and it sails out on its own, sails around. You give it a course, and it goes in that direction. It's smart enough to know when to tack and jibe and all that stuff. And so here's Sail Drone tracking across these natural slicks. And then here's the fluorometer that's on board Sail Drone responding to these very thin layers of oil as it crosses. So here we have a way of verifying, not only where the oil is, but what the real-time winds and currents are doing during an actual release, in this case, a natural release. The other application are the use of drones. And this is something that the Bureau of Ocean Energy Management is very actively involved with here. And what I'm showing you here are a little clip of video from experiments done a few weeks ago at the onset wave tank facilities in New Jersey. So this gives you a real-time picture, very closely controlled, so this thing can be driven around by an operator, ideally on a ship, and give a very exact picture of where the oil went. It can also be combined with different types of sensing technology, and you can see very clearly in here different thicknesses of oil which might be useful for responders. Okay, so some take-home messages here. This picture is taken from a spill which happened back in May, I believe. The Shell pipeline ruptured. It released about 2,500 barrels of oil. That was on a Friday. We took this picture on Sunday, looking down, and here are the response vessels. They got out there, they were in place, but as you can see, and the oil was pretty impressive when it was there, but as you can see, they're not necessarily targeting where the oil is. And I don't show this as a reflection or to disparage the efforts of the responders, just to say that it's damn hard sitting on the bridge of a ship to see, even when there's a lot of oil, where it is and where you should go. So imagine, if you like, that you had a little drone that you could launch and fly around and say, well, wait a minute, guys, you need to move the ship in the other direction and get into the right area. So there are some, these sorts of remote sensing technologies could very easily affect the thing. Satellite assets are useful in the post-incident appraisal, but they have fixed orbital schedules, and you can't always get satellite images when you want to. So I think that these drone ideas are very promising, but we need more field trials to make that operational. Okay, thanks very much.